Hello, everyone. It is a great pleasure to give you a plenary talk for this ICMSN 2025. My name is Bong-Joong Kim from GIST in South Korea. I will introduce an interesting and useful research area called Exsolution. The title is Real-Time Investigation of Metallic Nanoparticles Solved for High-Performance Catalysis. For the exsolution of metal nanoparticles, my lab specifically uses in situ transmission electron microscope, simply saying in situ TM, which is equipped with a gas flow system and a heating system as well. This system is shown at the left in the slide. We can monitor exsolution and phase transitions of nanostructures in real time while flowing controlled gas and applying temperatures. My lab also has a liquid cell system and a biasing system, as you can see the other images. Using the in situ TM systems, my lab focuses on understanding the creation and phase stability of organic and inorganic nanostructures and probing their properties in individual nanostructure device formats. As you can see, the selected journal cover images, we are working on not only catalysis, but also electronics, optoelectronics, and sensors. In this talk, I will highlight exsolution mechanism and kinetics of metals doped in metal oxides and its applications including CO oxidation, gas sensors, methane reforming, fuel cells, and photoelectrochemical water splitting. First, we need to discuss what the exsolution is. We normally dope transition or precious metals in perovskite oxides. So the metal dopants are placed substitutionally in B site here of ABO3 system. Then reducing conditions such as annealing on the hydrogen gas flow is applied to the doped oxide. Oxygen vacancies are created in the oxide matrix, and then the doped metal diffuses out to the surface of the oxide. The metal atoms form nanoparticles, as you can see the schematics, which is embedded in the oxide matrix, as you can see the figure at the bottom. Because the particle is embedded in the oxide, they never coarsen each other at high temperatures. So the particles are well dispersed on the oxide surface, securing stability of catalysis properties. This is a stark difference compared to the conventional catalyst systems. About 5 years ago, we watched exsolution phenomena and analyzed its gross kinetics using in situ TM. And this was published in JACS as a front cover paper at that time. We deposited cobalt-doped strontium titanium oxide films on silicon nitride special TM grids using pulsed laser deposition, forming polycrystalline oxide films. As you can see, the many grains. Interestingly, exsolution occurs at the corner, grain corners, and grain boundaries in vacuum, about 10 to minus 7 torr in TM. Thus, we can simply control the distribution of metal particles on the oxide surface as we control the size of grains. Further, we determine the kinetics of particle growth on the oxide surface. Based on analytical model we established here, the measured data we fitted finally, and we find that the gross kinetic is limited by a reactant limited model. We clearly observed that initially the exsolved particle grows very fast, and followed by saturation of the kinetics. Our in situ movie shows our entire results of the exsolution. I'm going to show you the captured movies. At 600 degrees C, we can verify the temperature at the note here. A few particles appear and the sizes are very small. But as increasing temperature, the size and density of particles also increase. All the particles placed at grain boundaries and corners. Occasionally, we observe diffracted spots of metal particles in FFT images. Using high-resolution TM images and EDX line scans, we clearly observe the exsolved nanoparticle is located at a corner of strontium titanium oxide grains because the location minimizes nucleation energy barriers using heterogeneous nucleation. We also find that during annealing above 450 degrees C, the cobalt particle is FCC structure, but it transforms to HCP structure at room temperature, where we use this particle for catalysis. Next, we measured the total volumes of the exsolved particles of the strontium titanium oxide film in a field of view of a TM image. As time progresses, at varied annealing temperatures, as you can see the images. Using the measured particle sizes here and the established model, we obtained the cobalt vacancy formation enthalpy is merely 1 electvolt, and the activation energy for the particle growth is 0.14 electron volt by fitting the Arrhenius plot as shown left. Moreover, by defining the equilibrium constant for the cobalt exsolution, we find that the enthalpy for exsolution is 2 to 2.5 times larger than cobalt vacancy formation. This is actually reasonable because the exsolution of metal elements occurs after forming oxygen vacancies in the oxide matrix under reductive condition. Importantly, we confirmed that particle coarsening never take place over 800 degrees C. Next published paper informs us how to form optimized size and density of catalyst via exsolution. Using ex situ experiment of cobalt-doped strontium titanium oxide film, we checked the conditions of several oxygen partial pressures and annealing temperatures. As you can see the images, the exsolved particle size decreases, and its density also decreases with increasing oxygen partial pressure and increasing temperature. Such condition increases reducibility. Using in situ TM, we further confirmed that the exsolved particle size decreases and its density increases as observed in the TM images taken from recorded videos. We also applied another parameter, which is temperature ramping speed, to control the size and density of exsolved particles. As you can see the series of SEM images, the particle size decreases and its density increases with increasing ramping speed. We try to understand the phenomena observed by altering three parameters: temperature, oxygen partial pressure, and ramping rate. Classic nucleation theory indicates that as increasing driving force, which is delta G, the critical nuclear size R star and the critical nucleation energy value delta G star decrease together. We can say that high temperature, low oxygen partial pressure, and fast ramping rate provide a stronger reducing condition. Finally, we confirm that the sample exsolved as stronger reducing condition actually gives a higher conversion ratio of CO oxidation. This slide shows a study on how to ease exsolution by weakening oxygen bond strength. This result was published in Energy and Environmental Science at that time. We used two different ways to impose tensile strain on the oxide matrix, which is here cobalt-doped strontium titanium oxide. One way of the two ways is applying in-plane tension to the cobalt-doped strontium titanium oxide film by inducing lattice mismatch. As you can see the figures at the left side of the slide. The calculated plot in the graph at the top left, the cobalt oxygen bond length and the unit cell volume both increase with increasing tensile stress. Also, the graph at the bottom left indicates in the tensile strain ranging from 0 up to 2.5%, cobalt vacancy formation energy is lower than other elements such as strontium and titanium. All the three elements of cobalt, strontium, and titanium are bonded with oxygen in the film. The other way is applying isostatic tension by adding larger A-site atoms here. From DFT calculation, same as lattice mismatch in the tensile strain ranging up to 2.5%, the cobalt vacancy can form favorably comparing to strontium and titanium. Therefore, DFT calculation proves tension from lattice mismatch and adding larger A-site atoms effectively increase exsolution tendency. With this theoretical result, in order to form tensile stress on the cobalt-doped strontium titanium film, we used dysprosium scandate, which is DySCO3 substrate, which has a larger lattice constant than strontium titanium oxide, and doped barium element into strontium titanium oxide. These approaches generate tensile strains in plane and isostatically, as you can see the XRD data. After reductive annealing, cobalt particles form on the strontium titanium oxide surface, as you can see the TM image, and the cobalt concentration is selectively high at the oxide surface. Also, we find that cobalt-doped barium strontium titanium oxide presents higher conversion ratio of CO oxidation, as you can see the plot at the right top side. After publishing several papers on exsolution, we sought how to develop new systems instead of the common perovskite oxides, such as strontium titanium oxide, and how to accelerate exsolution. So we decided to use tungsten oxide and try to dope iridium to it. Surprisingly, the iridium-doped tungsten oxide nanosheets exsolve iridium merely at 300 degrees C, which is the lowest temperature for exsolution ever. We also used in situ TM to monitor the exsolution process, as you can see the image on the right side. Using FFT of HRTM images, we recognize that the iridium-doped tungsten oxide transforms from monoclinic to a tetragonal structure at merely 200 degrees C, which happens at 500 degrees C in non-doped tungsten oxide systems. This phenomenon indicates the lower the transition temperature of tungsten oxide phase accelerates the iridium exsolution at very low temperature. Using DFT calculation, we proved that the iridium vacancy formation energy lowers down when iridium is doped. Furthermore, we find that the tungsten oxide nanosheets on which the exsolved iridium particles form demonstrate excellent selectivity and stability for hydrogen sulfide gas, as you can see the gas sensing data. Next, we tried to utilize the exsolution technique for hydrogen production via propane steam reforming. We also tried in situ gas flow TM to monitor the exsolution of a rhodium dopant from cerium oxide at 500 degrees C under 10% mixed hydrogen gas flow, and clearly confirmed that the rhodium nanoparticles, whose diameter is less than 3 nanometer, were anchored on the cerium oxide surface. In particular, the Moire fringes from the nanoparticles clearly distinguish them from the cerium oxide. As expected, the rhodium particles were not coarsened during the propane steam reforming process carried out at 700 degrees C for 65 hours, leading to extremely high resistance against sintering and coke formation. Recently, we also find a way to improve oxygen reduction reaction called ORR using exsolution technique in a special way and published this in Advanced Materials. For this, we used lanthanum, strontium, cobalt iron oxide system and doped copper to it. During the observation using in situ TM on the hydrogen flow at increasing temperatures, we find that above 100 degrees C, the oxide surface became amorphous. As you can see, the lighter line on the surface with approximately 5 nanometer thick. Then at 400 degrees C, the doped copper atoms are adsorbed to form nanoparticles. We tried to use this material for ORR for fuel cells. The amorphous surface layer was highly robust, even over 700 degrees C, as you can see the data. So cerium strontium segregation was completely prevented. So we achieved excellent activity and stability over 120 hours. Up to now, we have discussed exsolution from oxide crystals, typically manufactured by physical vapor deposition techniques such as PLD. So metal doping concentration is limited to less than a few percent concentration because of the doping concentration limit. And literatures reported that increasing doping concentration creates abundant oxygen vacancies, thereby degrading stability of catalytic reaction over time. Recently, we created a new exsolution technique called amorphous exsolution. For this, we spin-coated a one-part solution of cobalt-doped strontium titanium oxide on the substrate. Then the film was annealed in a vacuum chamber or TM with increasing temperature. In situ TM allow us to observe that entire doped cobalt atoms are absorbed in amorphous strontium titanium oxide film from 600 degrees C to 700 degrees C, followed by crystallization of the strontium titanium oxide matrix film at 800 degrees C, as indicated by the diffraction data. This is surprising that entire cobalt dopants, whose doping concentration is up to 30%, are completely adsorbed with no oxygen vacancies. The adsorbed cobalt becomes cobalt oxide particles on the strontium titanium oxide film. So they form pipe to band alignment, which is beneficial for photoelectrochemical water splitting. So we compared amorphous exsolution technique with other techniques, such as a simple two-step solution process where the cobalt particles form from a solution on crystalline strontium titanium oxide film, and typical exsolution using a physical deposition. We find that the samples synthesized by amorphous exsolution, which is the blue-colored plot, surface those fabricated by other techniques for PEC water splitting activity and stability as well, as you can see the graphs at the right side. For PEC water splitting, iron oxide Fe3O4 is highly efficient on strontium titanium oxide system because it has a relatively small band gap, so observe a wide range of light wavelengths, And it forms also type 2 band alignment with strontium titanium oxide electrodes. However, it is well known that iron is strongly bonded to oxygen in strontium titanium oxide. So iron is not well adsorbed from oxide matrices. Nevertheless, we adsorbed entire iron atoms doped in strontium titanium oxide film over 50% using the amorphous adsorption technique with a slight hydrogen gas flow, 10 to minus 7 torr. We finally obtained a current density of 5.1 milliamps per square centimeter at 1.23 volt versus RHE. Stability over 24 hours. Such high performance can be achieved because amorphous X solution of iron requires a smaller activation energy barrier than crystal X solution, as shown in the landscape diagram at the right top. This is the end of the talk. Thanks for having this talk with you.